creating a reduction formula. Why do it? Reduction, also sometimes you might see the term recurrence formula. Same thing. Reduction formula, recurrence formula. But what it's really good for is when you've got integrals to a power, and if it's a really high power. So you may have noticed when you're doing parts and things like that, a lot of the times you're just lowering the power. Oh, I've got to do it again, but lowering the power and lowering the power. Trig integral is a classic for that. You know, in order to do tan to the power of 5, I needed to know tan cubed and so on and so on. So it allows you to bring the power down and then get something really manageable to integrate. Integration by parts very often is used to find the formula, very often. But don't be fooled into believing it's always going to be the case. Let's have a look at this one. I've got a definite integral, 1 to e of x times log x to the power of 3. We're going to create a formula for it. So I'm going to say in. So I is just saying this integral, n is the power we're talking about. And I just replace the 3 with an n. Now I want to reduce the power. So it makes sense. Apart from the fact integrating log x to the power of n would be tricky anyway, but it makes sense to make that u, because when I differentiate, the power will reduce. And in fact, we'll get n times log x to the power of n minus 1 over x dx. That means my dv is x dx, and so v is a half x squared. uv, there we are, minus the integral of v to u. But if you have a look at the integral of v to u, it is essentially the same, just that the power has changed. It's been reduced. So I can go and calculate the first bit, the square brackets there. I can substitute in the e. Log e, of course, is 1, and 1 to the power of n is always 1. So I get e squared on 2, minus, substitute in the 1, we'll log a 1, 0. So I just get e squared on 2. But then I have minus n on 2, and as I say, that integral is essentially the same. So I can say, well, actually, that's I n minus 1. It's the same integral, but now the power's n minus 1. And we've now got a formula that allows us to reduce these down to something manageable. So I'm working out I3 then. Well, what would I3 be? Substituted into my formula. E squared on 2 minus 3 on 2 times I2. Well, what would I2 be? Well, that'll be E squared on 2 minus I1. Well, what would I1 be? Well, that would be E squared on 2 minus a half I0. Now, I0, once I get it down to 0, well, log x to the power of 0 is just 1, and I'm now just integrating x, and that's very simple to integrate. And we get our answer. Another way of doing it is to, instead of reducing it down, is to build it up. So you could start with I0 and go, okay, I0 works out to be a half of e squared minus 1. Then I build it up. I1 would be e squared on 2 minus a half of that answer I just got. So it's e squared on 4 plus a quarter. I2 would then be e squared on 2 minus I1, the answer that I just got. And then I can get to I3 by doing that. And really, it's a preference. Do you want to work down and reduce, or do you want to build it up from the bottom? Probably the reducing down would be by far the most common way of doing that. But yeah, there's no reason why you can't build it up. Integration by parts, by far the most commonest way of, commonest, is that a word? Anyway, it's the most common way of doing it, but not the only one. Trig, for instance. So if I've got in is cot to the power of n. Well, if you remember from our trig integrals, the tan, and therefore the cotan as well, we use the same technique every single time. Didn't matter what the power was. So why not just use that method here? And that method, if you recall, is, well, I'll pull out the cot squared, because the cot squared I can change to cosec squared minus 1. I can split it into two integrals. The first one I can do via a substitution, so u is cot x, u is minus cosec squared x dx. But the second one, look, it's the same integral, but the power has been reduced. Let's finish off our integration of the first bit, and we've got ourselves a formula. Now they want us to use it to go and find what cot to the power of 6 would be. Before we do that, another way of doing it, certainly with trig, because of trig identities, then try in plus or minus the n plus 2, because the trig identities, the squares, so it's an idea. You might not see it straight away with something like this, so you probably wouldn't. But when it's a question which says show that, and you notice you've got an integral plus the sum of I, okay, maybe what I'll do is I'll move that I to the other side and see what happens when I add these two together. Anyway, let's have a look at how I could do it with this one. So what I'm saying is, okay, well, what would in plus 2 be? If I add them together, I get cot to the power of n plus cot to the power of n plus 2, which is cot to the n outside of 1 plus cot squared, but 1 plus cot squared is cosec squared. I've now got derivative times function, so I can add 1 to the power over the power, and then just rearranging that, I get in plus 2 is equal to this, but I want a formula for in. That's all right, I can still use this formula. I'll just replace n with n minus 2, and then I get the formula. So everywhere I see n, I'll put in n minus 2, and it brings it back to a formula for in. It's just an idea that sometimes works. Okay, let's go and do the second part of that question now. Let's go and find I6. I6 minus a fifth cot to the power of 5 minus I4. I4, but it's negative I4, so I get plus a third cot cubed plus I2. I2 brings it down now to I0. Well, I0 would just be the integral of dx, which is x. So certainly once these powers start getting very high, a reduction formula can save us a heck of a lot of time, because we're not going to have to continually doing the integration. The formula, if you like, is doing the integration formula. Again, integration by parts, you might use it, but you might have to use other techniques as well. Algebraic manipulation, trig identity. So here we go. Given that in is this particular integral, 1 plus x squared to the power of n, find a formula that does connect in with in minus 1. Let's find it. Okay, that's in. I want to reduce it down, so I'll make u equal to 1 plus x squared to the power of n. If I differentiate that, because that'll get the n to n minus 1, and they're telling me the formula is going to involve n minus 1. The v is dx, v is x. So I got uv, that bit's fine, minus 2n x squared 1 plus x squared n minus 1. Not quite the same as in. I've got this x squared in front. Now I can do some manipulation. If I rewrite that x squared as 1 plus x squared minus 1, I can split that into two integrals and have a look what happens. The first integral becomes 1 plus x squared times 1 plus x squared to the power of n minus 1. The second one is just 1 plus x squared to the power of n minus 1. Well, hang on, that middle one is 1 plus x squared to the power of n. Now both of these integrals are in the form of what we started with, it's just the powers. I've got minus 2n in plus 2n in minus 1. Move the 2n in to the other side, divide by the 2n plus 1, we have a formula that we can now use. So yes, I use parts, but also I had to use some algebraic manipulation as well to get the answer out. A very, very old HSC question. In is the integral of cos to the power of n this time. And they've told us the answer, which is great in an assessment, because if we can't find the formula, then we're kind of screwed for the next bit. Because if I haven't got the formula, how the heck am I going to do it other than going through the whole process and what have you? So if I couldn't get it, at least I can go do the second bit and work out cos to the power of 5. But we're going to get it. In is cos to the power of n. This is different than a tan one, because we use different techniques depending on whether it's an even power or an odd power. So which one do I use? I don't know, because I don't know if it's odd or even. So I will go to parts for this one. Cos n minus 1, cos, I'll make it two parts, they're both going to be coses. Why did I pick n minus 1 and cos x? Well, they've told me I'm going to end up with n minus 2. The power is going to end up n minus 2. What would I differentiate to get n minus 2? I would differentiate the power of n minus 1. So that seemed like a logical thing to make u. When I differentiate it, there's cos to the n minus 2, and I know this is going to be involved in my answer. dv is cos x, integrate, I get sin x. Okay, let's see what it looks like. uv plus n minus 1 integral of cos n minus 2 sine squared. Now we've got a bit of work to do to get it to this form. Having a look at the square brackets there, that's nice, because cos of pi on 2 will give me 0 when I substitute in, and sine of 0 gives me 0 when I substitute in. So that square bracket is all just 0. I'm left with this integral. Sine squared I can change to 1 minus cos squared, get everything back to coses. Split it into two integrals, and now they're both cos to the power of something. So I can rewrite that as in minus 2 and in. Move the in to the other side and divide by n, and we've got the formula that they want. We have our formula. But that doesn't finish it. We now have to work out power of 5. Here's what I was talking about here. They've given us the formula for this one. So I know it involves n minus 2, so maybe I'll investigate in minus 2 minus in. Let's see. Substituting in, play around with it, I've ended up with cos n minus 2x sine squared x. Really, it's not going to save me a lot of time. I'm still going to have to use parts to get this out. So possibly not a good approach for this one. But anyway, let's keep going with it. uv minus v to u, and we eventually get it there. Was it quicker than the other way? I don't know that it really was. It didn't really save me that much time. Let's evaluate our I5. Well, that'll be 4/5 I3, which will be 4/5 of 2/3 I1. This one I have to stop at 1, because remember we're going down by 2 each time, and so we can't go to -1. Cos to the power of 1, but that's still a nice little integral to do. Integrate cos, we get sine, substitute in, and we get our 8/15. Alrighty, 2 years ago. Jn, just to mix it up a bit, why always use I? Let's use J. Is the integral of x to the power of n e to the minus x. Nice starting point. We just simply have to work out J0. A little gift mark to start off with. So, okay, all I've got to do is substitute 0 into the formula. Let's see what happens. And it's just e to the minus x. Integrate e to the minus x, I get minus e to the minus x. Substitute in 1, substitute in 0. Bingo! I've got the answer that they were looking for. Thank you very much for that, Mark. Okay, show that Jn will always be less than or equal to 1 on n plus 1. Here's how I did it. Well, I know x is going between 0 and 1. Now, why did I choose that? Well, they were the limits on this integral, and there had to be a tie into it, so, okay, that's what I'm interested in. But that also then means e to the minus x is going between 1 on e and 1. Hang on, where did I pull that one from? I've applied the function e to the negative x to all parts of that inequality. I could do that because e to the minus x is continually decreasing, which means that the inequality sign changes. And that's why you might be looking at it and go, what? See how I've swapped them. The 0 became e to the power of 0, which is 1. But I've swapped it because it's a decreasing function. The 1 became e to the minus 1, which is 1 on e. Swapped it because it's a decreasing function. So remember, your inequality signs are preserved if you're applying an increasing function over the interval, but they'll be swapped when you're applying a decreasing function to the interval. Now that I've got that to work with, remember Jn was this expression. We want to show it's always less than or equal to 1 on n plus 1. I know it's always going to be less than or equal to x to the power of n, because in between 0 and 1, e to the negative x is always smaller than 1. Well, that's 1 on n plus 1, x to the n plus 1 from 0 to 1. Substitute in and we get 1 on n plus 1. So yes, Jn is always less than or equal to 1 on n plus 1. Show that Jn, so now we're going to create a reduction formula, is n Jn minus 1 minus 1 on e. Okay, there's Jn. It pretty much looks like, yeah, we're going to have to use parts here. We've got x to the n and e to x. So I'll make u equal x to the n, because that will reduce my power down. That's what I want to do. And that means v is e to the minus x. So v is minus e to the minus x. uv minus becomes plus. V to u, substitute in 1 and 0, that becomes minus e to the minus 1, and my integral, well look, it's pretty much the same, just the power's been reduced, so I have the formula that they're looking for. Now, the fun part of the question. Using parts 1 and 3, show by induction, or otherwise, if you want to go otherwise, by all means go otherwise, this expression here. We want to show that. Going to prove the result's true. The first case in this one is actually 0, not 1. Sub 0 in, we get a whole heap of 0 factorials, which is 1. we get 1 minus 1 on E, and that's what we did work out was J0. So that is certainly true. It works for n equals 0. We're going to assume it true for k, and we want to prove it true for k plus 1. Okay, our proof. There's jk plus 1. Well, let's substitute in our assumption. Our assumption was for jk, so there it is substituted in. If I was to expand this out, well, k plus 1 times k factorial is k plus 1 factorial. And, there should be parentheses around the top of that fraction there, because otherwise it looks like I'm saying k plus 1 factorial. But of course that is k plus 1 factorial. Well, getting close. This 1 on E, remember, look, the k plus 1 factorial is fine. It now sits by itself. I know I want that. Everything else I want to pull into one sum. So I'm going to need this term here to have the same coefficient of k plus 1 factorial on E. So I force it and say, well, that's the coefficient. But how does it change this fraction? Well, I must have multiplied by 1 on k plus 1 factorial. Now it still becomes 1 on E. But now that both of these two terms have a common factor of k plus 1 factorial on E, I can now pull the 1 on k plus factorial into the sum. It would simply be the next term, because it's 1 on r factorial when it's k plus 1. So I get the sum that they're looking for. So hence it's true for k plus 1 if it's true for k, by induction. And then the last part of the question. Now use 2 and 4 to prove that E is actually this. With Jn, remember we proved it was less than or equal to 1 on n plus 1. I've added in the 0 on the other side because it's always going to be a positive amount. Well, we just found Jn was this expression. Okay, so I know that's in between the two. I want sum of 1 on r. Ooh, where? Okay, we're close here. I've now divided everything by n factorial. So in this fraction over here, it becomes n plus 1 times n factorial, which is n plus 1 factorial. And in the middle now, I have E minus the sum that we're looking for. But what happens if I take the limit of all three things as n approaches infinity? 0 is going to stay at 0. The right-hand side, well, if I've got infinity on the bottom of the fraction, that's going to go towards 0 as well. I've now trapped this in between 0 and 0. So I now know that actually that expression is 0. Well, if that expression is 0, I now move the limit to the other side, if you like, and there it is. We have that it's equal to E. Whoa, that was a good little question. Okay.